record. Okay, there we go. Let me scroll to the right place in my lecture notes. There we are. Perfect. All righty, let's switch back to the notebook. Prepared. Haha. Okay, so there are a couple questions right off the top. Yesterday's lecture capture, I posted it immediately after class, but then I forgot to publish the module for the week. So it wasn't showing up. It should show up now for those of you that missed yesterday. Yeah, we went the whole time, so please catch up on that because we did actually cover quite a bit of stuff. Shouldn't keep you from understanding today's stuff, except maybe some of the stuff at the very beginning. And then also there was no quiz yesterday since it was nominally still a recitation day. Today's quiz though is up now. 3 questions. You'll be able to answer them kind of as the class goes per usual. And then, yeah, I'll write that down, I guess. Quiz for today is up. And then next homework should be up tomorrow. I got a little bit busy today with some stuff, and it took me much longer to get down here than I was planning. Is that 6 or 5? I think it's 6, out tomorrow. Hopefully tomorrow I'm not saying the same thing, but plan on that coming out either tonight or tomorrow morning. And then lastly, what was the other thing? Shoot, what was the other thing? There's something else. We're back in person. Darn it, there's something big I was supposed to announce. I don't remember now. Quiz is up. Oh, for those of you coming into class, bring your laptop starting tomorrow. If you don't have notes. No, you do. Okay. Yeah, so you won't need the laptops today, but tomorrow we're going to be in Python notebooks. I'll post the notebook for tomorrow's class sometime shortly before class to try and get that downloaded, and kind of as you're waiting for me to sign on and stuff. Otherwise, I'll give you guys a couple minutes before we start to download that, get that set up. Yeah. Other than that, I think we're good to jump into stuff. Are there any other questions before we get started? Homework is not optional. No, it'll be due. I will, however, though, probably get you guys through the end of the class to finish it. So you'll have more than a week to do it, or whenever the kind of finals due, I'll have it due that day. So I think that's maybe the Monday after we're done in class, something like that. Don't hold me to that, but it's a few days after we're done with our in-session stuff. So
the final, like on the day of the final? Like
yeah, so the final, I haven't decided if I'll put it out a little bit before that, just in case there are any kinks with it again. At most, you'll have probably 2 days to take it. Probably 1 day, but we'll see. Plan on that being the day of the scheduled final, though. It'll be that, yeah, for sure that day, maybe the day before as well. It kind of depends on how the days line up and the grading deadlines when those are due. So stay tuned on that. It'll be very similar to your past final or past midterms. Won't really be any different. There will be a few more questions on the stuff we covered between now and then, plus lambda calculus stuff and parsing. So nothing too crazy. Your best source of review material are the homeworks and the quizzes. Mostly the quizzes, because a lot of the questions will be directly from the quizzes. There will be probably 10, 20 new ones, and we'll give you like 50 questions kind of thing. So it'll randomize. Everyone's midterm will be a little bit different from the other person's. I think you guys maybe noticed that. So cool. Well, if there are not any other questions, let's jump into it. Let me silence my phone because people are trying to call me right now. Okay. I should have put it over there because I'll forget it when I leave the classroom. Let's get started. So yesterday, and I'll just scroll up to remind you guys, we kind of covered the numbers in the lambda calculus, how we encoded those, how we programmed with those, and we worked some evaluations. Today, we're going to start with kind of talking about a couple more functions on the numbers. And if anyone maybe had solutions for times or exponent, let us know in chat. Don't necessarily post a solution yet. But we'll write out those, show you how those are done. And then we'll jump into how we do more general styles of recursion. Because so far, the only type of recursion we've done is what would be called, we're using what's called the recursors for a type. And we've encoded those directly into the types themselves. So like our numbers have a way of dealing with successor and zero. Our Booleans have a way of giving computational value to true and false through this kind of selection mechanism. It's very similar to pattern matching, except there are no patterns, right? It's just through function application. Today, we're going to do something similar, but it's going to have a more general recursive style. So it's unrestricted. You don't necessarily have to recur on, for instance, successor and zero. You could recur on, say, some result of a branch in if then else or something like that. So we'll play with that a bit today. And it'll probably be the most confusing topic you guys will ever see in your 4 years of college. It's a rather hard thing to grasp. I don't expect you guys to completely understand it the first time around, but it is something that is good to cover so you guys know what it is. You'll understand parts of it at the very least. So, but first, let's start with a warm up. So if you remember yesterday, we defined the plus function, and this was kind of our big thing of the day. And we said plus took this lambda n and a lambda k, and then we applied n to what? Was that the first argument or the second argument?
We applied it to K.
Yeah, we applied it to K and successor. And this gave us the result we wanted as far as addition goes, right? We did some hand work, some evaluations by hand, and it turns out it works like plus, right? And that's because n being a number, it's a function as well in the way we encoded it. And basically what happens is if n was 0, it would select K. If n is not 0, it would select successor, but apply successor to all of the inner terms in n, right? Because n could be a big stack of s's, right, of those applications. Now we're going to do something similar. So how do we define times? And I'll give you guys a second to work on this. This is harder. It's harder to let you guys work on your own when we're online, because I don't know if you guys are actually working or not. But I can look at Conlon and Aaron, and I can tell if you guys are working because they're scratching away. So how do we define multiplication in this style? I'll get you started with kind of the boilerplate stuff. So what do we think for sure we should have maybe at the beginning? We should probably give it a name. So we'll just call this times. We throw that equals there. We don't have anything on the left-hand side right now. And then what could we for sure put on the right-hand side? What could we for sure put on the right-hand side? Ooh, so yeah, Pascal has a good idea, maybe plus somewhere. We'll get to that in a second. But yeah, so a lambda n and a lambda k again, because we have to take in 2 arguments, right? Multiply is a function on 2 arguments, so we better have 2 arguments there. Boom, got our 2 arguments. Now what goes here? I'll give you guys a second to try and work that out. And a bunch of people are saying we'll probably need to use plus, and you'd be right. You do need to use plus somewhere. But try and write out the whole thing if you can. Should be a few parts. Pretty small stuff. It should be about the same size as plus. Anyone have any ideas of where we could get started? Actually, here's a question. So we have a few constructs we can use here. So we could either, and so here's some meta commentary. What could we fill in those question marks with? We're very limited. There's not a whole lot. We can use one, more lambdas. So more kind of function arguments being introduced. We could use variables. Or three, we could use some kind of function application. And with variables, I'll also put other definitions. Okay, so that's kind of the other thing that we could use as well. So we could like refer to plus, which we know we're gonna have to do. So Arthur's got an idea. And let's take a look at that idea. So I'm gonna write over here, Arthur says, maybe we could do something like this. So do n, k, and then plus n. What do we think of that? What do we think of that? So Linnea thinks we need a call to successor somewhere. Arthur's not so convinced of his own work anymore. But I'll say Arthur's somewhat on the right track. I mean, you got all the parts there at least, or most of the parts there. I'm going to go ahead and say we don't really need a successor anymore. Don't need a successor anywhere. So right here, if we kind of break apart what n's doing, right? So n takes something, n's a number, and it will select, if it's a 0, it'll select k. Okay, so n times k, kind of based off that, if I did n times k and n was 0, I would get k back. That's not quite right, I don't think. Right, because it ought to be 0, shouldn't it? What else could we do? So Arthur's, yeah. So Arthur has a new idea now. So he says now lambda n lambda k dot k n and plus n. What do we think of that? Oh, and Arthur had some reasoning there. So we can't have k in the final sum of all the pluses. We need k number of pluses. So plugging in plus n into each of the s's in k to get k. So basically the idea is that we need to add on n k times, right? Is more or less what he was saying there. Ooh, and I think he's got it now. I like this better for the most part. Here now, I think what he meant to say, if you're following along in chat, was lambda n lambda k, and when we do k z, or 0, not z, it should be 0 because z was the variable we were using, plus n. What do we think of this? What do we think of that? So let's break this down. If k is a number, it then selects something if it's 0, it selects something else if it's a successor, right? So if k is 0, what should it select if we're doing multiplication? K times n. and k is 0, what should our result be? 0. Right. So are we selecting the right thing there? Okay. Now how about here? If k is a successor, what should it select? Right. And then it's going to then make another call to the same thing, right? Because that plus n is going to kind of unwrap over k and just keep applying plus n, right? Oh yeah, reformulations on each line. I'll make that more clear. So they're not equal on each line. So this one's not right. This one's not right. Good question. Yeah, because I did throw the equals on each line. Let's copy this over too for consistency's sake. Cool. I like this answer. Let's carry out an evaluation and see how it behaves. Okay, we're getting used to this by now. So if I have, let's just do times 1, no, let's better do at least 2, 2 and 2. Okay, what does this unwrap to be? Well, we can definitely sub in our multiplication definition. Duplicate, bring that down there. This is going to get unwieldy fast, so we won't do the full evaluation for this guy, but we'll kind of get an idea of it. We'll leave this in white, and we'll just put a 2 over here and a 2 in purple over there. What's the next step we can do? Right there. How do we reduce that? What can we do there to reduce it? We have a big old lambda in here. We have a couple things out there. What does that mean? It's an application, right? So how can we reduce an application?
You mean like apply it?
Yeah, how do we apply it? What do we do?
Like KS of SC.
KS of SC. What do you mean?
Like to make it 2.
Oh, yes, right. Yeah. We could do that. Well, we couldn't do S of SZ. We do suck 0, right? Because S and SZ were those variables inside those definitions that gave them functional meaning. So here we're going to sub in we're going to sub in 2 and another 2 for N and K. Okay, so let's do that. So we're just going to copy over everything over here, duplicate. Okay, so now that K becomes a 2. It'll become the darker purple 2. And this N will become our pink 2. Great. Now note that we don't have any recursive call to multiply here, right? Because we're not allowed to. This is the part where the definition of numbers and the definition of plus take over, right? Because it's encoded into the meaning, how we handle these. Kind of hard to see the dark purple on a black background. Cool. I will change that color. Let's use green. Better? I haven't ever gotten complaints about the green, so okay. Bingo. Yeah, I'll try to use more bright colors. Sweet. How do we keep carrying this out? So how we could read this, and this is something we were kind of getting used to yesterday, is having a 2 there means we're going to select this one twice. Okay, we're going to do this 2 times. And then when we get to 0, we're going to do this. Okay, so what this becomes, we can think of these numbers as iterating a function, right? And so we can skip a bunch of steps here because we have some idea of how this works, how these evaluate. And we can leave this kind of expanded out as, well, it's going to be plus 2. And then here we're going to have a plus and another 2 and then a 0. Okay, that's if I expand it all out, right? Because we can think of numbers as iteration, right? They're going to iterate function application directly. It's how we've defined them. Cool. Anyone super thrown off by that? I'm not going to carry out any more than that, but I think it gets the idea across. So if you actually did the hand evaluation,
How you got
go ahead.
I'm not quite sure how you got that, to be honest with you.
Yeah, so this was something we went over mostly yesterday, is the 2. If we went and looked back up at the definition of successor, I'm gonna have to scroll up pretty far to find it. Here, we can look at this as, okay, I'm giving you a number. You know, there's gonna be that inner number, whatever successor is kind of wrapping up. And that's kind of similar to how it was in Scala as well. And then it's gonna take a Z and an S. Okay, so I think it's the number 2. It's got the thing it's wrapping up. And then we've also given it a value for the 0 case and a value for the successor case. It then will apply that successor function, in this case it's plus, onto whatever was left over, applied to the same thing again. So all the numbers are really doing is iteration of a function. That iterated function is going to be that S that we passed in. Does that sort of clear it up?
Yeah, a little bit. I'll just
Okay.
have to think about this for a bit.
Yeah, if you work a couple more problems with numbers, just by hand, even just some evaluations, you should start to get a feel for it. It's a little kind of counterintuitive, takes a little bit of wrapping your head around to understand, but play with it a bit and it'll become very apparent. So we just did times. We needed that for our other exercise today, so I better keep us moving. Otherwise, we won't get to everything. So now we're kind of moving on to how do we handle recursion in lambda calculus. So we're going to start with a little bit of a warm-up. We're going to talk a lot today about combinators. And actually, we're going to talk a lot of the next couple of weeks about combinators, the last 2 weeks of class, because parsing involves a different kind of combinator a lot. So I'm just going to give you a kind of a fast and loose definition here. C-O, that's an O. Combinators are small functional programs that are used to combine other programs. And you can think of program as function here. Program and function mean the same thing in this context. Okay, so that's like a kind of hardcore definition. It's a little hand wavy, but let's just give you an example so you can get an actual feel for it. So here's an exercise. Define the function K. We call this the constant combinator, or the K combinator. We usually write it as a bold K. Such that K of xy is equal to x for any x you give it. Okay, we call this the constant function. Okay, so given any input, it always gives you the same output. How might we write this? Should be a pretty straightforward function. Give it a try. There you go, Linnea. Sorry about that. You have an answer?
I mean, is it the same thing as like true? What we define as true is
Oh.
like lambda x, lambda y, just gives x.
You think it's the same as true? What does everyone else think? Ronak did the same. Yeah, so it's the same as true, right? You take a lambda x and a lambda y, and you give x. So it's kind of the same as both true and zero, right? What do we think about that? Do we think that's a coincidence? What are true and zero? Like when you think about those in terms of like induction or recursion, those are usually your what? If you're like writing a function on the numbers or the booleans. It's often your base case, your terminal. Doesn't require any like recursion, anything else to make sense of itself, right? There's a question from Pascal. Is that the Cartesian product? Oh, not the Cartesian product. That's the letter X. Yeah, I haven't. We don't introduce products here at all. So, yeah. So the latter, Pascal. It's the variable X, not like multiply or anything. Yeah. So we have this K combinator, right? Not very interesting, but it has some interesting practical application, right? So we could have just said like, oh, well, when we were defining those constructors earlier, 0 and true, we could have just said they're equal to K, and that would have been fine. We could have done that. Might be useful in the future if you kind of see where this is going. So the next exercise we need to do to kind of keep moving forward is, and I don't know if I love the idea of doing this because it could end up turning into, actually, I'm going to give you guys the answer for this one. So we want to write the check for if a church numeral is 0. Okay. Pretty straightforward function. This is the is0 function. I'm just going to give it to you. Otherwise, I think we'll get bogged down by it for a little too long. Where'd it go in my notes? There it is. So is0 is equal to lambda n. So it takes in some n, and it's going to tell us if that n is 0 or not. Okay. So n, and then we had the 0 case come first, right? We would have true, right? Because that'd be the 0 case. Otherwise, what do we put there? We're going to put constant false. Now, why did I put constant false there and not just false? Any ideas?
Sort of like what we were saying, that we would run that like function n amount of time, so it being constant doesn't really
kind of makes it not.
Yeah, it makes it not like.
What would it do if that wasn't there? So if I just had false there, what would what would happen? So what if I had written false there instead?
It would return false n amount of time. I feel like.
No. What it would do is it would apply false to itself a bunch of times. You'd get something really weird. I don't know actually what it looks like, but it wouldn't give you the right behavior. So we need to say constant false, which means as many times as you iterate this, it needs to be false at the end. Like forget all the other like successors. This is just going to end up being false. It doesn't really forget them. It just like, it'll cycle through. You'll keep applying it. So this is one of those combinators. We won't talk much more about is0. We'd need it just for our not next example, but a couple examples from now. We also have another combinator which might be useful in a minute. And you guys actually know this function quite well. This is called the I combinator. Can anyone guess what it is? I'll give you a hint. It takes one argument. Not the inductor. Pascal's got it. It's the identity. So often we'll call the identity the I combinator, the identity combinator. That's just lambda x dot x. Okay. So if you ever see me write a bold I, that's why. Lastly, could we write a combinator that like takes a function and applies it to itself? Could we do something like that? So like, write a function that, or a combinator, I should say a combinator there. Write a combinator that takes a function and applies that function to itself. Arthur, correct. Recursion is a no-no. Let me know if there's a place I used recursion. I don't think I've used recursion. Or at least recursion in the way we've used it, it's a no-no. But Arthur, elaborate on that if you have a thought. Yeah, so write me a lambda that'll take a function as an argument and applies that function to itself. Not recursion. Note it's not recursion. Because it's not referring to itself. Oh, so this is a good point. It's applying it to itself. It's not referring to itself in the definition. Those are different things. So for instance, I could apply, say like, I'm trying to think of a good example because it's a really kind of weird case. For instance, you could apply like successor to successor, right? And that would stack on and create like a number like 2, right? Or just a, you know, some other number. So you could apply something to itself in that sense. Does anyone think they have an answer? Very simple function. Yeah, so John's got a guess. And he said lambda x dot x x. Right, so you could think of that as lambda x applied on x. Like so. We're going to call this omega. The omega combinator. And it's a lowercase omega. That's important. Another combinator. Let's see. Yeah, so S of S, right? So if I did not SS, right? Because those are just variables, but if I did something like successor on successor, does that mean anything? That's actually a good point. What is that? Like if you were to give that a type, what would it be? So pretend we have types. What type does this have? A nat to nat. It's missing the nat that would go here, right? I don't actually, this might not work with successor now that I'm thinking about it, but well, does it? Yeah, no, does it? Yeah, this doesn't work with successors. That's a good point. This does not work with successor. Other than in the sense that you could apply it. Well, no, I think it does work with successor, but it wouldn't do what we think it does, I think. Yeah, so the type here would be, this would be a nat to nat, right? If I had a lambda there. Yeah, forget the successor analogy right now. I'd have to do some more digging to see if that actually works. just know this is kind of a weird formulation. You don't end up using it a lot, but it's important for theoretical results. And I'm sure there is a place where you could use it. It would be more in the situation where you're applying some kind of like high order function to itself, maybe, where it's like, I'm giving you a function, now do something with it, but do it to itself, right? So like you could apply omega, say, to, well, you could certainly apply it to K, right? And I think we do that in this next example. So what would something like omega K be if we were to just kind of carry it out? So what does that equal? Let's just copy the definitions over. And I'll make omega, we'll use red for omega. And let's use blue for K. Okay. And what was the definition of K? Well, K took two arguments, lambda X, lambda Y, and gave us X. Okay. Let's apply this. What does this give us? Okay, well, we can sub in this blue stuff for X, right? So I'd get that and that right next to it, right? Applying a function to itself. Oh, Arthur, I think this will clear up for you in a second then. I see where you're going with that. So what does this equal? What can I do here? Pascal says it resolves to K, not quite. It's going to end up resolving to, we're going to apply this will become X, okay? And we sub it in. This Y never gets an argument. So we end up getting, let me recolor this just so we can kind of keep this consistent. I'm going to actually swap this out for, this will make it more clear. So I have this part, and I'm going to rename this back to K. And I'll change it and make it green. Okay, so big K there. Then the whole thing, okay, we apply K for X. So now I have lambda Y dot K. Yeah, so here's the question. So does it matter that Y gets a value since Y is not utilized, right? Y doesn't matter here, but given what we know of the constant function, that's kind of the point, right? Is the constant function just kind of carries out some constant value. And so even given a Y, we still get a constant value if we apply K multiple times, even to itself. Does that kind of make sense? So it'll select that second argument no matter what. No, we can unroll this. No, and it looks more like lambda, we'll rename Y to Z dot lambda X dot lambda Y dot X, right? So it's still selecting some constant value. Yeah, and Arthur, where you were going with the thoroughness is, remember, in all of these calculations, we don't ever get like a finished result because the only fixed thing we have are functions. Everything's a function. And so applying a function to itself must work because it's just applying functions over and over again, right? And you can always supply a function to an argument. So there's not this idea of like data that we had before. Data is even a function in this sense, if that makes sense. And it might not. But that was kind of the example we were running with. The other one I want to show you with respect to omega is, what does omega I give us? What does omega I give us? This is kind of a weird one. Yeah, Arthur, right on. So Arthur says, so at the end of the day, omega k results in a 3-argument k function. Exactly. Just in that the second argument is the constant value. You could think of it just like that. So yeah, and Arthur's also got an answer for this one. So wi equals I, right? So if we wanted to kind of not skip steps there, if I want to write this all out, it's really quick. If I did omega I, that becomes I applied to I. If I substitute the first I in for its definition, I get lambda x dot x on I, and then I just get I, right? So right on. Good work there, Arthur. Did anyone else start to get that? Or is maybe close? Okay, so now I have another fun question for you. What if I did like omega omega? What does that equal? Okay, we call this function big omega. What does this equal to? So let's walk through this together. This will be lambda x with x applied to x, and then another one, lambda x with x applied to x. And then what can I do here? How do I carry this out? Well, I'm going to apply this and substitute it in for x here. Okay, so we're just doing an application, substitute that in for that, and it gives me lambda x dot x for this x, and this x becomes lambda x dot x. Wait a sec, can we reduce that? Do we know how to reduce that? We just did it, right? What do we call this in programmer lingo? It's an infinite loop. So we even have a combinator for infinite loops. That's pretty cool. Is there any practical application to this big omega guy? Maybe a detection for infinite loops? That's an interesting thought. I actually don't know if there's, I asked that question not knowing the answer to it. That's something academics aren't supposed to do in class. Well, I guess we kind of are. Yeah, you could do kind of an event listener. This does represent infinite loops pretty succinctly. Now, like, what if you gave it something else? Well, yeah, what if you applied something to omega? I don't know if it would do anything with it because it's a complete term.
Could be like, check the runtime.
Yeah. Well, I don't mean what we could use an infinite loop for. Yeah. I have a computer science degree too, guys. I took all those classes. No, I mean, like, I don't know actually if you could use omega for that though, without modifying it a little bit. I think you could use little omega to iterate. That would be okay, but I don't know if you could use big omega on its own, which is the interesting part. So like, I think what you would do if you wanted to do like an infinite loop with a game loop, you would do something like omega. Oh wait, that's too big. You do something like omega on, we'll call the game loop G omega, right? So like one cycle of game loop. Does that make sense? And then what would happen is this would copy this. Ooh, wait, does that work even? So that would copy that and it'd give you a G omega and a G omega. So that doesn't really work either, does it? Because then this would apply to that. There's a way you can write that. So you could use little omega, I think, to do that for sure. But I don't know exactly. Maybe we need to switch these two around. That might be the way to do it. Maybe if you did that. I'm not sure. Major bonus points if you can figure out a way that makes that work. That actually might be some bonus points. I might have to work that one out in my free time. I'll probably forget, but it would be an interesting little dive to take. So yeah, so we have this interesting like looping behavior now. Well, wait, does anyone remember what's the difference between loops and recursion? Ooh, Arthur says WW omega equals WW. Arthur, I'm having a hard time following that notation there. Assuming WW equals X. The 3 X's threw me off a little bit. No, I get that. That part makes sense. The equal signs are confusing me a bit. Arthur, I will revisit that. WW equals XX. Yeah, I'm not sure. Yeah, Arthur, follow up with me after class about that. I'm not sure where that's going. I lost my train of thought. Oh, right. So if we had big omega and it's acting as an infinite loop, and I said we couldn't have recursion, but aren't recursion and loops the same thing?
I don't know. I mean, like recursion is sort of like more like a while loop because it terminates on something.
Well, a while loop can be an infinite loop if there's nothing terminating it, right?
Well, same thing with recursion.
Right.
Recursion.
But it could be, right? And we've just shown you have infinite recursion, and that's the most unbounded kind, right? So could we, if we have unbounded recursion here, do we think we could recover bounded recursion? Especially given that I'm a teacher in a class and I ask leading questions all the time.
I feel like
Probably we can, right? So yeah, so it turns out we can kind of recover recursion in a really interesting way. So let's try and write something like the factorial function. Let's start by writing it in the way we're used to it. So I could write factorial like this: fact of n equals if is 0, n will give you 1, else we'll do what? Multiply, which we just defined, n, and then what? N minus 1, fact of predecessor n, or n minus 1. We don't have a minus 1 function, but kind of pretend we do for a minute. And then we might start off with, sorry, catching up on the notes. So we could write this whole thing maybe as that if that we wrote the other day, but with, maybe we say lambda n. We could write all of this right now, except for the factorial part at the end. Everyone with me there? But now we get stuck because we have a factorial on both sides. That's a bit of a problem. What if we factored out the factorial and made it like the result of an application? So what if I did something like factorial is equal to lambda n, or sorry, not just lambda n. What if we did lambda f dot lambda n, and then we had the if is 0, n, 1, and multiply n. And then here we, instead of putting fact there, we put f, and then the same n minus 1, and apply that whole thing to, I need to write this better because this is going to get really confusing if I leave it like this. I'm going to change the color of this one. So the green brackets mark the end of the entire expression. There should be one more paren there, I think. And then we apply all of that to factorial. Those are equal, right? Everyone's with me there, or is that maybe confusing? Those are the same function. Conlon says that's okay. Are you really okay with that?
Yeah,
Right. Are you okay with that? Okay, so the two folks in class are okay with this. I'm assuming everyone online is.
And we don't have to say like what n would be.
No, because n's just that numerical argument. So for now, we can just leave it there. Yeah, but now factorial is kind of like passed in as an argument, right? So we call what we just did, the stuff in green, we call that something special. We call this the fixed point. I'm going to change this all to green. And I'm going to duplicate it. And we usually denote fixed points with a big phi. Okay. Now, what is a fixed point?
It's like when you have a function and you just keep applying it and applying it and applying it on its own output, eventually it will stick at a point and it won't move from there.
Nice. I like it. That's awesome. I wasn't actually expecting an answer to that. So I'm going to write this formally, and then yeah, that actually is a really good kind of general idea. It's the idea that when you keep applying a function, eventually you hit what we call a fixed point, something that is kind of this stable thing that when you keep applying the function, it stays there. Okay, so formally we define this as, we would say a fixed point is any x such that some f, some function on that x, or some particular function, is equal to x. And I should say for a given function f. F of x equals x. So what happens if I would keep applying f to this, like say x? It would just always be x. So you can kind of think about it as this local spot where there's an identity, right? It's not really an identity, but you can kind of think, oh, it's in this spot, this function behaves just like the identity, right? But just in this spot.
Like if we call factorial though, it's not going to be at x. That value is going to
Oh yeah, so let's revisit this with respect to factorial. So in this case, how would we write factorial in this sense? When we apply the green part, phi, onto factorial, that's equal to factorial. Are you convinced by that? Maybe not. Not I, sorry, phi.
Why would the f of x always have to be x? So then are you applying a function on that x and then spitting out a different value that isn't x?
No, this x is the same as that x. Now, why is this the same or different here? Here our x is factorial. Oh, sorry.
Oh,
Yeah.
I see.
Oh, wait, maybe I, 1 second. Did I tell you the wrong thing's the fixed point? The fixed point is the x part. So here factorial is the fixed point, not phi. Phi is not the fixed point. I goofed that up. Got that mixed around. Phi is the function, not the fixed point. Here x is the fixed point. I reversed those when I originally explained that. Yeah. So phi is a function with a fixed point. Right, and that fixed point here is factorial. When I apply phi to fact, it gives me fact, right? And are we convinced of that fact? Because that's the really important fact here. Fact. So if we look at this here, and I'll start using highlighter. If we take a look back at this thing, that's the phi part, right? I have fact here being applied to the phi, and it equals fact, right? I've just copied that down there. Okay, that cleared up for Aaron. So that's neat, right? And it turns out we have this neat thing called the fixed point theorem, and it's a really cool idea about the lambda calculus. And it says, for all terms in the lambda calculus, there exists some term, I should say some term, in that calculus and I should have done letters as we were going. So for all terms f, there's some term in that calculus, and we'll call that term x, such that f of x equals x. Where we call x the fixed point. Where x is called the fixed point of f. Check out for everybody. So what I've said here is that for every term, there exists a fixed point. Why must that be true? Yeah, Pascal has a good point. So does this mean that every program will eventually stop? In some sense it does, but only in some sense. And now this is why I asked that. Does this have a fixed point? Well, it's itself, right? No matter how many times I apply this, it still spits out the same thing, even though it never terminates. It's its own fixed point. Down here, if we kind of think about this with respect to other programs, what if I do something like, let me think of a good example. What is a good example? I'm like really blanking today on coming up with examples. Like on the function, let's say plus I don't know. I'll come up with more examples. It's not coming right now. My brain's tweaking. But yeah, in a sense, it doesn't necessarily say every program will stop, but it says that every program will give you a fixed output that is, or every program has some input that will give you an output that is the same as the input, no matter how many times you apply the function. There's a lot of words. But it just means everything has a fixed point. Otherwise it wouldn't terminate. So it's almost kind of converse is true. The function wouldn't terminate if there wasn't a fixed point, right? Our base values, our base cases for functions. The reasons that we have base cases is because of fixed points, right? There's a fixed point somewhere, and then it's able to conclude, right? Let's see. I have 10 minutes to wrap up, and I think I'm going to kind of hand wave through this because you'll need this part for the quiz. For any, so do fixed points exist for some subset of possible inputs to F, or is the fixed point such that it would exist for any possible input of F? For some input of F, not all inputs. It's just for some input, right? Yeah, if it was for every input, we would have a problem, right? At some point. Yeah, so like for instance, if I did, what's a good example? Crap, I'm not coming up with it today. Like the function multiply. If I multiply by 0 and keep applying multiply by 0, I always get the same result, 0. That's an instance of a fixed point, right? So it's just some input. But I need to keep moving, otherwise you guys won't be able to do the quiz today. Yeah, I'm going to do some hand waving here, introduce us, and we might actually start with this tomorrow because I'll need to explain this more. We have something called the Y Combinator. The Y Combinator captures this idea of a fixed point in kind of the abstracted way. It just captures the essence of it. And we'll define Y to be lambda F dot lambda X on F of XX and then that whole thing, or not the whole thing, but that, and I'm running out of room now, applied to itself. And something to note about this, Y on some F, so give it some function for that F, is equal to F of YF. It constructs a loop, is essentially what this does, is it duplicates a function. And now to wrap things up, and I think we'll unpack this more tomorrow and actually talk about it more, is if we wanted to define factorial in terms of this Y Combinator, what we would write is factorial n, or if I'm kind of being consistent with my stuff, factorial is equal to lambda n on Y with that big phi from up top, n. And I'll leave that for you guys if you want to carry that out tonight. Otherwise, we'll revisit tomorrow and actually carry this out and show that it gives us kind of a recursive factorial definition. So we'll pick that up there tomorrow. But that gets you everything you need for today's quiz. So yeah, we'll pick up there tomorrow. We'll just have a little bit to wrap this up. Bring your laptops up if you're coming into class, because we'll be jumping right into parsing after that. So yeah, have a good night, everybody. Otherwise, we will see you tomorrow.